Good afternoon. My name is Sophia Nunez, and on behalf of our team at Caresoft, I would like to welcome you to our Parallel Works webinar, Driving Space Excellence, Orion Strategy with Parallel Works Activate.
Great to have everybody here. We are going to be talking a little bit about what Parallel Works does and our Activate software technology. And then we have some really interesting discussion planned with Orion Space Systems and the work they've been doing generally kind of in the computing domains and the work they've been doing using our technology and a bunch of interesting Q&A to follow. So look forward to it, and thanks for joining. A little bit about Parallel Works. We sit in a world of complexity, computing complexity specifically. We've grown the company over many years, focused on really trying to harness diverse computing resources from a lot of different architectures and geographies. And you can see on the page here, today's enterprise computing infrastructure is rarely just a single monolithic system. It consists of a lot of different types of infrastructure, and it's becoming more and more challenging for organizations to be able to kind of wrangle these things and make them usable for the people that need them, the scientists, engineers, developers, model builders, et cetera. So a little bit about the company. We spun out of Argonne National Lab actually about 10 years ago to the month, focused on commercializing supercomputing workflow technology. And really what that means is we were a software user interface on top of batch scheduler supercomputing systems like the one you're seeing on the screen here. Over the years, as hyperscale cloud, AWS, Azure, Google, Oracle, and many others started to catch up in terms of performance to these on-prem systems, we were one of the first companies focusing on bringing supercomputing HPC uniformly across all these clouds. And what that led us to was really being the operating system for hybrid computing systems. So hybrid means that the computing systems you may operate internally inside of your boundary, and then those externally, so the hyperscale clouds and others, having those work together in unison. And we're seeing a lot of that same type of capability be needed for enterprise AI systems and big GPU clusters that organizations are buying or renting now. So if you look at what an organization looks like today in terms of their computing, and some organizations may only have one or two types of these sorts of computing infrastructure. Others may have all of them or even more. And there's a mix of infrastructure types that consist of token-based LLMs now, GPU providers, cloud providers, there's edge systems, there's virtualized environments. And what happens right now is end users get placed onto these systems and they kind of get siloed away. So you have your developers maybe that are working in the clouds and the ops people that are sitting over in the virtualized edge environments, the analysts working with the LLMs and the GPU providers. What Parallel Works and our Activate control plane does is kind of cuts through that complexity, and it really aims to connect all these systems together, make them appear as a single system. And so when the end users actually have to get on and access it, they have to just understand how to interact with our software as opposed to all these various types, which everyone has a different interaction point. So kind of put a different way, we're a piece of software that sits on top of these wide varieties of computing infrastructures and just brings them all together into a single interface and bring a number of capabilities on top of those things, like controlling the variable costs that occur in many of these type of systems, allowing you to schedule workflows and tasks, computing tasks into one place, which then get abstracted away into all these other locations. And by doing this, you can we help organizations build their own killer apps, so to speak, their own applications, create their own data products. We're going to have Orion talk about the really interesting work that they do, which kind of fits right into this as well. Just in terms of an example deployment of how organizations use our system, we have a SaaS platform that anybody can kind of get in and start using very quickly. You can plug your own cloud accounts into, and then we act as a provisioner inside of your own cloud. In some cases, like the one you see on the page here, organizations can take our entire software and move it inside of their own boundary, either on-prem or in the cloud. And, once that's deployed, we become really the front door or the bridge for the end users to access whatever variety of infrastructure your organization may have. And so in this example, this company had 2 data centers across, one on East Coast, one on West Coast. They wanted to use those first, and when they needed burst capacity, they wanted their end users to seamlessly burst out, and that's kind of what our Activate software is designed to do. If you just want to talk about 2 use cases more in the federal sector, we've been working with NOAA R&D, the RD HPCS organization, for several years, and they operate a program running a lot of cloud cycles through the platform, and we act as their front door for both their on-prem systems and the cloud, the multi-cloud environments. They have thousands of users accessing that, or have access to this system, and that's been kind of running successfully. Another one is for the Department of Defense, the mod program. We've taken our software, moved it into a FedRAMP High impact level 5. So for export controlled software and data, end users can come into this environment and get seamless access to the defense supercomputing systems, of which there are many, as well as these IL5 ITAR ready cloud environments. And what this allows is any DoD user or contractor to come in, click a button, get an IL5 or FedRAMP High ready cluster at within a few minutes, which is very different than the current business as usual of having to go through a full ATO process that could take 12, 18 months and sometimes millions of dollars. So that's my little intro on ParallelWorks. With that, I'm going to transition it over to Orion. I think Junk was going to talk next, and he'll talk about all the great work that they have going on over there.
Yeah, thanks, Matthew. Appreciate that. Hopefully you guys will be seeing our slides popping up. And I really appreciate you guys inviting us to be a part of this conversation and to share some of our experience. I'm going to provide a quick overview for a few minutes of Orion Space and what we do and a little bit of how we do it. And then I'm going to turn it over to one of our principal research scientists, Dr. Jeff Steward, who will go through some concrete examples of how we're actually running Activate in order to do some really complicated physics-based modeling of the space environment. So big picture, Orion Space Solutions is about a 20-year-old company now. We are part of a larger family called Arcfield. So we are an Arcfield company now. We are a new space company. We do a lot of development of sensors. We've flown a variety of satellites. The picture that you're seeing on the screen here, there is a little piece of Orion hardware, which I will kind of highlight here, and we'll highlight it again in a future slide, that is actually flying on the International Space Station up there collecting data on the space environment. So we've got a wide variety of experiences there. We've launched small constellations of microsats, and then in the particular portion of the business that I lead, we do a lot of modeling with all of that data. So we really focus on that near space environment, and we really try to think through what it is that end users need to see, what decisions are they trying to make, how is the space environment going to impact their mission or their organization, and then we try to build custom applications that really help them make whatever decisions they're trying to make and or understand the impacts of the space environment. So generally speaking, we've got a variety of strengths here. We're really good at building very difficult things. So we like to work with organizations like DARPA, who you may be familiar with, the Defense Advanced Research Agency. And they have a little saying where they really only take on the very hardest problems. They even give it a name. They call it DARPA hard, meaning it's so hard that they don't think anybody else in the world can do it, because if somebody else could do it, then it's really not a DARPA problem anymore. So it's a great organization to work with. We love working with them. And one of the satellites that you're seeing on there on the left side of the screen is actually a DARPA mission that was flown several years ago, where we built a spacecraft on a size and on a scale and with a set of instruments that just nobody thought that could be done. And we were really excited to do that. And we are supporting them on several other programs even today. In the middle there, you're seeing that you can see that little white outline. That's one of the sensors that Orion built about 5 years ago that is now flying on the International Space Station. And it is using signals of opportunity that come from the GPS constellations. So think of GPS or the other ones that come from other countries. And we are using those as signals of opportunity in order to make some measurements of the ionosphere. We can measure the total electron content within the ionosphere, and we can also measure the reflection of those signals off of the ocean. And with that reflection, we can measure the waves on the ocean. We can measure their wave direction. We can measure their wave height. We can measure the sea state, all from a space-based platform. So you can imagine there are plenty of users in the world, especially the United States Navy, who might like to know what the sea state is in various bodies of water around the world, and we can support that. And then finally, we pull all of that data with all of that sensors and we integrate those into models. So this little flying carpet video, we love to share this, is from one of our sensors called Tidbit. As far as we know, we're the only organization in the world that can measure the ionosphere in this particular way. So what you're seeing is a very complicated wave pattern. This is not a model. This is actually visualized data that we collected, visualizing one specific layer of the ionosphere over a relatively short period of time. So as you can see, the ionosphere moves in really complicated ways that actually looks an awful lot like the surface of the ocean. And there are a lot of similarities between how the ionosphere responds to various things in space, mostly solar events, and how the ocean responds to a variety of things like wind. And when boats travel through the surface of the ocean, they leave a wake. And when spacecraft travel through the surface of the ionosphere, they also leave a wake. And so we can use that as a measurement technique, for example, to better understand what's happening in low Earth orbit. Definitely one of the areas of current research going on right now. Generally speaking, we cover a wide variety of the electromagnetic spectrum. So as you're seeing here, we're trying to depict that at very low frequencies, at very long wavelengths, like 100 meter wavelengths down at 3 megahertz. We have sensors and missions and models that work down there. And then all the way up at the ultraviolet, when you're into the hundreds of nanometers from a wavelength perspective, we have sensors and we have models and we do things with everything along that entire electromagnetic spectrum. We're pretty excited about that because we think that entire electromagnetic spectrum contains really vital information for decision makers and has a way of predicting a variety of space environment and space weather events, depending on where you are in that spectrum. Generally speaking, we start with really hard scientific problems. So what you're seeing on this screen is a little bit of a pedigree of some of our programs where, up to 20 years ago, we started with some really interesting sensors. So having an understanding of the environment, we know it can design and can think through, well, what is it that we really need to observe? What exact phenomenology is necessary that isn't already being collected by a sensor out there somewhere? We can then design that sensor in whatever portion of the electromagnetic spectrum is applicable. We can then build that sensor and deploy that to remote and austere locations. We've got sensors operating in Alaska. We've got sensors operating on the Big Island of Hawaii. We've got sensors on the International Space Station. So when we say remote and austere, we really mean remote and austere. And then we can transport that data. And you can imagine the compute capacity required, not just from a data transport perspective, but now I've got to store all that data because I've gone to an awful lot of trouble to deploy a sensor to a really difficult location. So I don't want to lose it. So data security becomes very important to us. And then I'll need to use that data in a model that's probably never been designed before, because if it had been designed before, we wouldn't have bothered building that sensor. So we build a new model and we figure out how to visualize that. We have to typically run that in what we think of as operationally relevant timelines. So it doesn't do us like an Orion. We don't really focus on the analyzing things that happened several years ago. One of the differences in the operational world versus the academic world is in academia, it's very common to study a solar storm, for example, for several years, if not decades, after that solar storm has already passed. In Orion, we really focus on trying to understand what's happening in space right now. So, as you can imagine, that does drive some of our compute requirements. One of the models that tries to answer that question that we were pretty proud of is called Dragster. I think we're familiar with that image on the right side of the screen and the fact that there are tens of thousands of objects in space, more so now than there ever has been in the past. In fact, in the last 5 years, more satellites have been launched in the last 5 years than had been launched in all of human history prior to that. So space is getting really crowded. I know that's not new news to most people on this call, but it certainly has implications for the need to better understand the environment and the need to have a variety of improved tools. Dragster is one of those. So unlike most other tools that really try to focus on space traffic management, we can actually measure the uncertainty of several of the key variables. And we do that by running an ensemble of models. And we could not run an ensemble where we've got hundreds of models running simultaneously unless we were able to do that with extensible cloud computing and HPC or high performance compute type architectures. Naturally, we're a bunch of space physicists. We're not a bunch of Oregon National Lab trained computer scientists. So when it comes time to run those high performance compute loads, we really appreciate having a partner in ParallelWorks and having a product like Activate, which helps us focus on the physics and not have to worry so much about dealing with that control plane for all of those compute architectures. There's another model that we like quite a bit. Let me get to it. There it is, called Mazda. Mazda is a model that we use for the electromagnetic portion of space domain awareness. It models the ionosphere, which is also coincidentally in low Earth orbit, but it really has a strong impact on any kind of radio signal. So whether you're trying to communicate with satellites or whether you're trying to get data down from a satellite, you have to make sure you understand what the ionosphere is doing right at this moment and how the ionosphere is going to impact whatever signal it is that you're trying to either transmit or receive. So Mazda is another one of the models that uses a lot of the data that we collect with the sensors that we designed, and it runs in a high performance compute architecture, and it provides real-time information to decision makers who are trying to understand, how do I talk to somebody, halfway around the world in a valley in Afghanistan? That's a hard problem, and understanding how the ionosphere is affecting your RF transmissions is essential to being able to solve that hard problem. So we're excited to be able to be a part of that kind of a decision-making process. Generally speaking, in addition to collecting and doing all that high-performance computing, we then have to deliver our data to somebody who cares. So we've got a variety of customers. We make that data available through an API, and naturally, the security of that data, the continuity of that data stream, of that REST API, and the overall high availability of that data is essential to our value proposition. As a business, if we were unable to continue to meet the requirements of our customers, they wouldn't be our customers for very long. So that type of reliability and that type of scalability, the ability to move back and forth between high performance cloud computing and on-prem computing as the time requires, all of that is essential to our business model. And it's something that we just can't afford to make a mistake ourselves with. So we really rely heavily on ParallelWorks and on Activate in order to help us solve that critical problem within our particular ecosystem. So now to demo a couple of these models, I think in a little bit more detail, I'm going to turn it over to Dr. Jeff Steward.
Well, thank you, Junk. I'm happy to be here, and I'll go ahead and share my screen here. And so we will go ahead and tell you guys a little bit more about what we do at Orion and how we use ParallelWorks Activate. The space weather, as Junk mentioned, is a very complicated phenomenon that is very heavily driven by the sun. So this is a visualization of the thermosphere, which is where low Earth orbit satellites fly. The ionosphere, which Junk had mentioned, is also coincident with this, and that's the portion of basically the same part of the atmosphere, but where it has been ionized. So basically making it, change its substance and have a lot more E&M properties that are important for communications and things like that. So the ionosphere is a very important part of the thermosphere. And so here we visualize this, and we will actually run an ensemble of different potential scenarios for the thermosphere as well as the ionosphere to try to understand kind of what's happening as a function of time. So we have what's called a digital twin here, where we're running a lot of different members of an ensemble. And the way to think about an ensemble is a bit like the multiverse, and popularized in like the Avengers and things like that, where you have slightly different versions of reality, and they all have equally plausible potential outputs that could happen. And so those are not that much different from a video game in terms of what we're actually trying to simulate here. The real science comes in where we start to have observations. So observations are actually what make things real. And once we start to basically combine that together, the stimulation with what we think the space weather might be like in terms of all of the possibilities going on there. Once we combine that with actual observations, then that starts to become a reality, and that's through data assimilation. So satellites fly through this space environment and are affected by the thermosphere as well as the ionosphere. They also sense that. But one of the main ways that they're affected by it, one of the most direct ways that the satellites are affected is actually in terms of their orbits. So the orbit calculations that are going through here are very complicated. They involve a lot of different terms. There's that saying, it's not rocket science. Well, this technically is rocket science. And so what we're showing here is we're showing a satellite along with a uncertainty bubble, or you can kind of think of this as like an electron cloud of potential places that this could be. So going forward in time. So what we've done here is we've taken actual observations of a satellite, at 1800 on October 14th, 2024. And we've actually propagated that and taken what we knew where it was, and we moved that forward in time using all the physics of orbit dynamics and all of those kinds of things, as well as our understanding of what's happening with the space environment. And as that goes forward in time, you start to like lose track of where your satellite's going to be as a function of time. So this bubble will grow in time, and this basically represents what is actually happening with the satellite at a particular point in time. So I'm going to reset to fly through to here. And one of the things that we're not the only one who obviously care about space. There's also a huge amount of conjunction analysis and basically making sure that space traffic management is taken care of. And the 18th Space Domain Squadron of Space Force actually also tries to keep track of these things. So they don't have quite as sophisticated of sometimes of the actual physics that are involved here. So a lot of times they will need to create a little bit larger bubble when they're doing these orbits here. So let's go ahead and fly to this, and we will see here. This represents the 18th Space Domain Squadron, what they actually use for conjunction analysis. This very large safety bubble, and they're definitely trying to make sure that they err on the side of caution here. But this is about 25 by 25 kilometers in about 2 kilometers in height. Whereas we're able to, using our physics with a relatively short lead time, we're able to get this down to the order of meters to understand where that satellite's going to be. So you can imagine if you have 2 different satellites flying through, or 2 different even debris objects, and you're trying to say, what is the uncertainty here? If you're using this relatively large ellipsoid here, with another relatively large ellipsoid, you're going to have a lot of messages that say, hey, I'm really worried here that there may be a collision or a conjunction. So if we actually come in here and turn this off, when you actually do this, you may be a lot less concerned, right? That, okay, I'm pretty sure I know where my satellite's going to be. with this amount of accuracy. And very interestingly, it does ours does take into account that there's more uncertainty in the what's called the along track of the satellite, so the direction it's traveling in, because that's where most of the drag calculations actually end up coming in. So in this direction, we're at this time, forecast time, we're actually uncertain about 600 meters in the along track direction. In the cross track direction, we're only uncertain about 33 meters. And in the radial direction, meaning the height direction, we're only uncertain about 24 meters. And these numbers are actually driven by how well you knew your satellite at the beginning. If you didn't actually know your satellite that well, so this satellite happens to have GPS, very accurate, what are called ephemerides, or position. So we knew where the satellite was pretty well. If you use less accurate kinds of computations, then you may have a slightly larger uncertainty bubble. So this one in here, we're actually, because we started from a less certain, we didn't have the GPS precise orbital information, our uncertainty is about 5 kilometers here. Yeah, basically all of this is to say that we can create these uncertainty bubbles around our satellites, and by flying a two-way digital twin of, we have a digital twin of the satellite, which a digital twin, if you're not familiar, is a replica. So we have a replica of what that satellite is going to be experiencing. We make sure to track all of the physics that it's actually going to be relevant to that satellite. We also have a digital twin of the environment. And so with the digital twin of the environment, the thermosphere and the ionosphere, as the satellite flies through these simulated environments, we can see where we think the satellite's going to be at any one point in time. Then when we actually have an observation of that, we can say, well, we thought the satellite was supposed to be here, and this uncertainty bubble is supposed to represent like 95% of the time we think the satellite's going to be within this bubble. If it usually, 95% of the time it will be in this bubble, assuming everything's well validated and everything like that, which we strive to do. Then once that happens, and we say, okay, well, actually, since we know that the satellite is here, we no longer need to have such a huge bubble. We can shrink that bubble and move that around. So that's the process of data assimilation, reconciling the model with the observations. And these two digital twins together basically allow us to do a lot of different use cases for customers, such as satellite antenna time planning. So if you're a satellite owner operator and you want to calculate, okay, I need to schedule my antenna up to the second, because it's very expensive time to do downlinks and uplinks, then you'll really want to know where your satellite is going to be at a given time. And if you can forecast that out more in advance, that's very beneficial. Another thing is more accurate conjunction assessments. So if you get an alert from the 18th Space Defense Squadron that said, hey, I'm really worried that these two things may collide, it's very helpful to understand ahead of time, like, what is my real risk here, given what I actually know about these two different objects in the catalog, and being able to more accurately assess the risk there. And if there is a significant enough risk, then you may need to make a maneuver. But the earlier you can make the maneuver, just because of the way orbital dynamics works, the wider that spread can be. So if you wait till the last minute, you may have to burn rocket fuel, or delta V. Whereas if you can, actually wait until, or if you can get ahead of that sufficiently, you could potentially do a rotation or some other, reconfiguration of your satellite to have your satellites pulled in or something like that. And that may be sufficient to avoid that collision without spending delta V. So all of these kinds of use cases are kind of together, what we call Orbit IQ. And this helps us to understand all these different use cases and solve a lot of problems for our customers. And a big part of this is the ParallelWorks use cases here. And I'm just going to share my screen. This is a presentation we gave to NOAA. And I'm just going to show some kind of canned things, because when you're working with the cloud, it does take some time to negotiate with the cloud service provider to get all those satellites in, or I mean, not the satellites, to get the actual infrastructure that you need. And so we'll just show the demo here. But this is the Activate platform itself, and we will start and run clusters in the cloud as if we had them on-prem, as Matthew mentioned, so that we can actually run these ensembles of high-performance computing through the Activate platform, and be able to basically run these on demand, which is very helpful for our digital twin scenario, and then explore, analyze, visualize that data, and actually use it to solve customer problems. So yeah, I think with that, Matthew, we can maybe go to you if you want to kind of lead us in more of a Q&A type style approach here, and we can just have more of a conversational style. So I'll stop sharing for now and turn back over to you, Matthew.
Great. Yeah, thanks, Jeff. I think we're all going to get on camera now and just have a discussion about state of computing within Orion and industry as well. Okay, yeah, that's pretty cool. I actually haven't seen that Orbit IQ in a while too. Pretty cool. I have some questions on that I'll get into a little bit later. So I think we heard what Orion and Arcfield is doing now. And what I really would like to start with is talking about how your computing journey has evolved over the years, where it started. Because I think we've been seeing this trend of organizations moving away from like big monolithic systems like, oh, I have a data center that I'm going to run into things that are much more distributed across various geographic locations, and some internal computing, some external. And I want to know if you're seeing similar things and kind of where you started from as well. Did you start in the big, batch scheduler HPC systems? And can you talk a little bit to that?
Yeah, happy to take that one. Yeah, you're absolutely right. When we started 20 plus years ago, we started with laptops, right? Like, what can I do on my laptop individually? And then what can I do networking some of those things together? Very quickly, we realized, based on the amount of data that we were collecting, that we needed storage solutions and compute solutions that far exceeded what we were going to find in a local laptop. So we started to kind of build our own little data center. We built out our server room. We started adding racks of compute. We started adding racks of memory. We eventually started thinking about GPUs. We've bought some of the bigger NVIDIA, like H100s and A40s, and integrating all of that into the architecture. And not too far into that process, we realized, boy, there's a lot of cyber vulnerabilities here. There's an awful lot of, power and other types of costs associated. I need a dedicated air conditioner, for goodness sakes, in order to keep my computer room cool. And all of that was necessary because, we needed that much compute power to assimilate all the data that we were running, to run all those algorithms that Jeff was describing. But we realized that our costs were growing exponentially for maybe what would be a linear increase in our individual compute capacity. And that became kind of our driver to move to the cloud. So I think we're not unique in that sense. I think many organizations have realized that maintaining servers and maintaining those OSs and patching them when new updates come out, that's just not their core business. And they don't want to be in that business. And they don't necessarily want to have a PhD and 20 years of experience at Argonne National Labs in order to do their core business. So they kind of needed some help with that. And we definitely fell into that category. So at first we talked with AWS, and we have an account there, of course. And then we talked with Google, and then we talked with Azure, and we, to some degree, wanted to work with all of them. And then, of course, we realized, well, gosh, the very bit of software that you deploy in one cloud, and, it can work in another cloud, but you have to tweak it just a little bit. And you have to have just a little bit different, kind of architecture in this cloud instead of that cloud. And again, we came to that same realization of, man, I don't want to have to be a 20-year expert in cloud computing. I want to be a physicist. I want to do the stuff that we do, and I really would like to outsource that, and I really would like to offload that requirement to somebody who is absolutely a pro in that. And so our relationship with Parallel Works, I think, started at that point with our realization that, hey, I don't want to have to do this myself. I want to find somebody who's become the world's leading expert in that. And naturally now we have this. See, I don't know if it's seamless yet, but we're certainly getting to the point where it's almost seamless, where we do have multiple cloud services running simultaneously. We've got on-premises NVIDIA GPU cards. We've got massive amounts of on-premises storage, and we are integrating all of that using the Activate platform, so that, at least from my perspective as an executive, when I hire a new astrophysicist, he doesn't also have to have a PhD in comp science. He can do the astrophysics part and the comp science part is handled mostly by you guys. So that's kind of been our journey, going
Yeah,
from
that's
there to here.
interesting. You described the transitioning from on-prem to cloud, but you're still leveraging on-prem resources for some things. And I know we've talked a little bit about this on the GPU availability and capacity side. What is the purpose of the on-prem systems today, like in your overall pipelines? Is it more development? Are you running operational things? Or just to maybe touch on that for a minute?
Sure. Yeah. So there, as you kind of go through, as any company goes through its kind of journey to higher ordered levels of computing, you eventually realize that there are some things where on-prem resources are cost effective, right? If you're going to be running a consistent workload over a long period of time, it actually gets pretty expensive to rent that from the cloud compared to just buying that capacity. A great example of that is if you can parallel process things in a GPU, even as expensive as an NVIDIA H100 GPU card, they're definitely not cheap. But if you're going to use it consistently for a long period of time, it's actually cheaper to own it than it is to rent it in that particular case. And in some of the models that you're seeing that we kind of demonstrated, we are running workloads pretty consistently. Like that dragster model has been running consistently. We basically turned the switch on, if you want to think of it that way, back in February of 24 and have never turned it off. So for that workload, if I'm going to be running and remodeling the thermosphere every 15 minutes, it is actually cheaper to store all that data on-prem and to parallelize that processing and run it in our own GPU card. Other models, like the Mazda model, we kind of run on demand, where we will do a really fast, like I want to know exactly what's happening right now, and then I want to be able to shut off all those resources and basically save money. That's the ideal workload for cloud, right? And so in our environment where we want to be able to do both, and we want to be able to do them, appropriately given whatever the cost model is, I kind of need a control plane that abstracts away all of those decisions and allows my scientists to just go in and say, hey, this is what I need. This is how long I need it. This is the performance I'm looking for. Go, and then have that abstraction layer go out and find the optimized compute environment to run that specific load. And naturally, that's where your product comes in.
That's what we do. Yeah, exactly. And there's, other control planes out there, but yeah, we see ourselves as that leading bridge to your, your end user base that you're talking about. So that's great. So kind of moving, that's pretty interesting. I think that trend is happening, and we're seeing it take place even in multiple directions when organizations build up a large cloud presence. Exactly what you said. They want to bring some of that back on-prem. I think I want to shift a little bit more to the application side. And Jeff, you showed that the Orbit IQ digital twin interface interacting with large-scale computing resources, I would imagine, to get those uncertainty quantifications around each satellite to project where it's going to be. Can you or Junk talk a bit about what is the actual workload itself from a computing perspective look like in terms of, getting the data in, you're doing data assimilation, I presume, you're spinning up resources to actually do this thing, and then then the data is getting into that interface in some capacity. Can you just talk about the different steps involved in doing that?
Yeah, so the digital twin is designed to have 3 different use cases, and they each have their own kind of places. So one of them is a what now situation, where we're keeping track and we're trying to do our best estimate of what's actually happening in real time right now. The second use case is what next. So we're actually trying to forecast that out in time for 3 to 7 days, depending on what the user actually needs. And the third one is a what if scenario. So being able to go through and say, well, if there was a large solar storm, what would happen? If I lost this satellite, what would be the impact on my processing? So a lot of things that have traditionally been lumped into, either OSSI, observation system simulation experiments, or wargaming kind of scenarios in the military. So a lot of these 3 different things. So there's different workflows for all 3 of these. And there's also different, within each of those 3 workflows, there's also different levels of, between development all the way up to production. So let's start with the what now. So that one is where we're really trying, like you said, to get the most recent observations that we have for Dragster and some of the other satellites that's actually pulling down their orbit ephemerides and actually trying to understand where the satellites are as opposed to where we predicted they would be. For Mazda, that will be ionospheric observations such as ionosons and radio occultations coming from GNSS satellites. So all of these observations together, we need to get the most accurate, up-to-date ones that we actually can in order to get the real-time information. So there's very much a window in which we have to actually work with the observations. If they come in too early or too late, we really can't use them necessarily. So within that assimilation window, once we have our observations, then we do need to kick off ensemble runs to basically understand how things are going to be forecasted in time, what the predicted satellite locations are, compare those to the actual satellite locations, and then or other observations. What is the difference in the observation space? Then project those basically back to our model space or our geophysical space to understand what did changes in neutral density or electron density or neutral winds or whatever other geophysical variables we're forecasting would have led to these changes. And
that with the different ensembles in that case is representing their different input conditions, and you get basically different uncertainty that way. That's what forms
exactly yeah. And then so going through all of that, and we need to run these models on demand to basically update the ensembles and say here's the new uncertainty. And then so like as I mentioned for the what next, that is basically running those out in time. So we say, let's run these out for 7 days, these models out for 7 days. We do have a deadline because people want to see, the new forecast. And then the what if scenario, that is very much on the fly. So people will want to play with the data and say, oh, I'm interested in this. And then that one is really, really important to have an elastic compute capacity where you can say, okay, are you willing to pay the cloud service provider here to answer this question? And if so, then let's go out and get you the compute resources that you need. And let's visualize that in that same pane of glass, the same digital twin. So you're seeing, essentially our best guess of what would happen if that were the case. And then for the 3 different levels of, between development and production. So when we're doing development, a lot of times it's very handy for us to have Jupyter notebooks where we can our scientists can actually go in and do a lot of the development they need to do and kind of play with it in that Jupyter lab setting. And then we also will run that in API mode. So where that'll be a call. And then we do have the operational mode where that's getting called on a regular basis and needs to complete within a certain time window. So basically those are kind of the different levels of the workflows we look at.
Oh, cool. That's helpful. Yeah, I mean, I think it's interesting as you're describing the gap from like the development and research stages into actually getting those things into production. Do control planes like the one that we create, does our platform have a place in that world as well, the actual transition from research to operations? And what does that kind of look like? This is more of a interest question.
Yeah, it definitely does because, so we can go in with the Activate platform and spin up the resources that we need and do our, all of our profiling and all of our development and say, okay, I'm trying to get this model to interact with this other model. So let me tie these together. We use directed acyclical graphs to represent these different outputs using Parcel, and you guys did help us out a lot with that process and understanding how the best practices there. So then once we have our DAGs developed through Parcel, we will then take those out of Jupyter Notebooks and prepare them for the same exact workflows to be run in operational mode or near operational mode, like staging mode and then operational mode. So yeah, it's
okay,
essentially
cool. So I see there is like a transition path from the research and operations with that. Okay, that makes sense.
Exactly. Yeah.
So I got another point here. A lot of the data that you're presenting and ionosphere forecasting and these type of things and the data products you're generating, I can imagine that they fall into different security compliance requirements. And I'm sure you're talking about DARPA engagements and there's things you're probably not able to share and all that type of thing. Can you talk about how, and maybe this is one for Junk, interacting with the computing environments across different security requirements takes place in your organization today? Because that is one area where I see a lot of complexity where it's like, oh, we need to run this thing in an enclave that someone's providing, or this input boundary condition is export controlled and we need to like run it over here. So how does that work within your organization today?
Yeah, great question, and you are absolutely right. First and foremost, man, it's complicated. So back in the day, right, so maybe about 10, 15 years ago or so, any kind of government workload like that, the government absolutely insisted it had to run on their hardware, and it had to be inside, a secure facility. It had to be run on a secure network, and it was very challenging in many ways to try to integrate commercial capabilities and data that was available over the internet into these secure enclaves and secure environments because they were air gapped for a reason, right? That was how they protected themselves from intrusion, and that was how they, protected the data that was inside those networks, was to make sure there was no connection between them. Over the last 10, 15 years, we've seen this real strong migration where the Space Force, especially the ones that we work with the most, there's this strong push where they really want to leverage commercial capabilities. They've kind of come to, I think, terms with the fact that they can't do as much by themselves as they could do if they were willing to work with all the commercial, both space companies as well as data providers like us and just other commercial capacity within the United States. Like we've seen with space launch, right? Like SpaceX is launching more total mass to orbit than every other country in the world. Just that one company, right? So naturally, the Space Force sees a huge value in working with commercial industry like that. From our perspective, what that means is our data that is running on a commercial network and commercial internet needs to figure out a way to get into those very secure enclaves. So we have to have a very trusted API. We have to think about the data security associated with that API. And then we have to enable the types of secure handshaking algorithms that the government networks and our networks can have that very tightly coupled and secure interface. There are still places in the government where the government prefers that the algorithms themselves are run inside their enclave. And so part of our challenge is sometimes the government will say, hey, I really like the algorithm. I really like the software that you guys have developed, but I need you to deploy that into my environment, into my secure enclave. And oh, by the way, I need you to feed it, meaning that the raw data that you're using in your commercial application, I want you to make sure that you can feed that same raw data into my secure enclave. So that's a whole different kind of challenge.
Is that actually a focus area within Orion now, actually taking these models you're discussing and deploying them inside a secure enclave? Yeah. Okay.
Yeah. And so naturally, the government being the government, they have some really complicated guidance. They call it the NIST 800 that describes exactly how secure an environment needs to be for a variety of reasons. And so, yeah, there are different levels, right? And so we have to be capable of operating across all those different levels of the NIST. Sometimes they call it the information security level, or IL level. So we do everything from IL2, which is basically commercial internet stuff, all the way up to IL5 and 6, which is that boundary between that ITAR or export controlled stuff and that secure secret level processing. And we have to be able to, our software has to work in that environment. Our data has to flow across all of those boundaries. The calculations have to be accurate and verified and validated in all of those environments. And that's a huge challenge. So having a templated solution that is appropriate for each of those environments that meets each of those security controls is just essential to what it is that we're trying to do.
Well, that's interesting. I don't know if you've actually tried to run in our high security platform yet, but that's an IL5 environment. If your thing runs in there, it's already ready to run. That's a probably offline discussion, but okay.
Can't wait to hook it up. Yeah, would love to.
Yeah, cool. All right. I didn't know you were actually doing that, because I know that, and I've been seeing this trend in Space Force with like the TAP labs and a focus on private industry building out, data products, I think, outcomes basically, as opposed to worrying about the models and how you're getting to those decisions.
Yeah.
And, and that's where like the shift from where the actual computing takes place, from like, oh, everything has to happen inside of this boundary because we need to own the whole stack. It's more like, I need an API to tell me the outcome or something. And that is that trend been happening for a long time, by the way?
A long time, I would say, certainly over the last 4 to 5 years, there has
Okay,
been this
all right.
trend in industry where the government has realized they don't necessarily need to own the entire satellite or the sensor, or in our case, they don't have to own the compute environment necessarily. They don't even have to own the model. They are happy just to receive the data, as you were describing. But they still have a lot of questions about, well, how secure is that environment? How secure was the data? Can we trust it? You know, did some foreign bad actor try to poison the data in some way that will corrupt the model? So we need to be capable of, number one, defending our systems, and then number two, providing that assurance to our government client.
Yeah, this will be my last question here, and then we can open it to any questions in the audience and whatnot. But what you just described, this kind of movement to, you know, data or outcome-based solutions as opposed to worrying about the underlying mechanics or models, I'd imagine that collides a lot with AI ML technology, and, you know, using trained models to get out that have been validated to then inference and provide those recommendations much faster than maybe having to run a full physics code. And maybe this is a question for Jeff, but is that, or, and I don't know who, but are you seeing that trend happening as well, where like what was once physics-based models is now being overtaken by AI prediction models? And if so, how are you guys leveraging that today?
Yeah, I think that is definitely a part of it. We work with a lot of scientifically minded people, and they're a little bit skeptical, I think for good reason, of some of the new AI ML technologies if they're too much of a black box. So very much we're interested in and pursuing and demonstrating for our clients explainable AI ML technologies, and that surprisingly, the physics still has a really big role to play in that, to make sure that we're doing all the scientific vetting that's necessary there. I think most people realize there's a potential promise there, but needs to just make sure that we understand what it's doing, how it will react to different like black swan events, and just have a little bit better understanding of how all of these predictions ended up where they ended up. And so we've demoed some of those solutions for some of our clients, and they've been very, very pleased with understanding, okay, well, now I know actually what it's doing under the hood, and now I can compare it back to other existing algorithms. So that is something that I think is almost a prerequisite for wider adoption in our neck of the woods anyway.
Right. Yeah, very interesting work. I think that is the last question that I'll ask, and maybe if there's anyone from the audience that has one. Otherwise, can kind of wrap up here. Thank you very much for your time. I'll maybe pass it off to Sophia to wrap things up.
Matthew, Junk, and Jeff, thank you so much for your presentation. I would also like to thank all of you for joining us today. We hope that you found this webinar was informative and helpful to you and your organizations. If you have any questions or would like to request more information, please contact our Parallel Works team via the information displayed on your screen. Thank you again for attending, and have a great day.